So the last thing I want to talk about in chapter 6 of our modern physics book by Taylor is this idea of the wave of velocity, or the velocity of what's called the wave packet. So before we said that a wave packet was actually just a wave, a combination, a superposition of many waves such that they eliminate the regions on the outside, and we're left with this kind of envelope of waves added together inside of this little packet. And so if I ask, what's the speed of this? What's the speed? Because that, if my wave packet now represents my particle, what's the speed of this particle? Well, let's take a look at it. If we start with something like, let's say all of the energy is kinetic energy. It's a free particle. There's no potential energy. There's no forces involved. It's just a particle flying through outer space. So its energy is its kinetic energy, which in a classical sense, not using non-relativistic energies, it's the momentum squared over 2m. Okay, but we also know that from Planck that the frequency is the energy divided by Planck's constant, which in this case is now p squared over 2mh. The wavelength is h divided by the momentum. So if we put those two together naively, then the speed of our particle, or the speed of our wave, I should say, is the frequency times the wavelength, which is now the momentum divided by 2m. Which, if I think about it classically, what happens with a particle in classical mechanics and non-relativistic classical mechanics, the momentum is the mass times the velocity. Therefore, the velocity of a particle is the momentum divided by the mass. So now we're in a conundrum because our wave packet, our wave analysis tells us that its speed is 1/2 the speed of a particle. So now we're stuck. Because if a particle in quantum mechanics is really just a bunch of waves added together, it seems to be moving at half the speed of if it was just a little lump of mass that Newton thought about in classical mechanics. So what's the problem? Well, the problem is the way that we're thinking about this wave packet. This wave packet is not just a bunch of waves which are moving in this direction. We have to take into account that all of those waves are individual. So this equation here is if we just assumed a single wave, that for some reason that is just one wave moving around the room. But that's not what it is. Our wave packet is hundreds, thousands of waves added together to give us a nice, concise packet shape. So instead we have to think about something what's called like the group velocity. What is the velocity of all of the waves running together? Well, it turns out that group velocity or the velocity of the whole packet is found by taking the derivative of the frequency with respect to the wave number. Because there's now, there's a change in the wave. We have many waves. We have, lots and lots of waves added together. So what we're looking at is how are those waves essentially different from each other? Because if you think about it, if we were to take essentially one wave, right? If we were to make all of the waves, if the wave speed is the same for all frequencies, so every single wave moved at the same speed, then what you would have is something that would be essentially a constant. That if So if all waves move with the same constant speed, right, then our definition of omega would be the wave speed times the wave number. I take the derivative of that with respect to k. This wave speed is a constant, and the derivative of k with respect to k is 1. And so if all of them have if every wave has the same speed in my packet, then that would be the speed of the whole wave system. So essentially, my wave packet, which I've drawn here, is a combination of many different waves added together like so. And each of these different waves are now moving with their own speed. So therefore, we have to take into account the variation, the change in frequency with respect to number, to figure out what the actual wave is. So if we use this definition of basically the wave pack moving, now we'll apply our quantum mechanics. So in this case, the energy is h bar times omega. The momentum is h bar k. So dE is h bar d omega. dP is h bar dk. And so another way of looking at this wave pack velocity is to write it as the change in the energy with respect to momentum. So if I do that and then add in our classical definition of this, then the derivative with respect to momentum, the derivative of the energy with respect to momentum is P over m. So in the end, the velocity of the wave packet, the group velocity of the wave packet, is our classical particle velocity. So you have to think, if you're trying to think about this particle, I'll draw it one more time, as this big group of waves, what we have to think about is how each of the individual waves that add together to make this packet, how they're sloshing around as the whole thing moves. So it's as if you can kind of see, as the waves are moving up and down and they're adding constructively. And so in the end, what you have is kind of this wave packet which is riding along as the waves change their frequency to kind of keep it adding together. So I wish I could draw a picture of that, because essentially what we have is all these waves added together. So let's say this is our wave, and this is another wave added to it. And so essentially, what if we had these things interfere constructively, and I'm sorry, destructively, until you get something like that. So what you have is something that looks a little bit like this. And then as these blue and red waves basically change their frequency, as they change form, you get something that is more like this. Where now the wave packet is over here. And so from our perception of it is that this wave packet has now moved with a velocity v. When in reality, all we've done is modify the frequency of each wave to get them to kind of add up destructively and inconstructively at different places in X.